Hi, everybody, and welcome to today's class. We're still dealing with chapter 30. Actually, we didn't finish it. We barely started it last time, actually. We just got the magnetic field of a solenoid. We have two types of solenoids. And today we're going to build an extension on that and basically discover the concept of transformer. Actually, more than that, we're going to discover the inductance, okay? So this is in a nutshell, basically. Once we do that, we're going to introduce the inductor, and then we're going to do the RL circuit and the LC circuit. This is quite a bit of material to be covered in chapter 30. There's a lot of things to be done in chapter 30. Okay, so let me share with you the screen. Again, for those who are not here, this recording is going to be made available, but you have to understand that this chapter is critical for what comes next, okay? Especially when it comes to circuits later on, okay? So this is extremely important stuff that you really have to have a handle over in terms of trying to understand how to handle the voltages and the voltage drops and everything else, because it has importance, first of all, for chapter 30 by itself. It has extreme importance for chapter 31. And chapter 31 is going to represent one of the main topics actually for this exam, how to deal with an AC circuit and how to basically write what looks like it's Ohm's law actually for an AC circuit and understand the RLC oscillator or the RLC circuit in that case. So this stuff is extremely important and it has applications in engineering. It has a lot of applications that are coming down. So let's get into the ideas from chapter 30 again. Share the screen. So far, basically what we have discovered the magnetic field created by this type of solenoid using Faraday Lenz law. No, I'm sorry, using Ampere's law. Actually, we used Ampere's law outside, found the magnetic field to be zero anywhere outside, and we found the magnetic field to be some finite value inside. There was a problem, actually, I hope that you guys caught it. The magnetic field has a wrong direction outside. It's not pointing up, it should be pointing down, actually. So because of the fact that it comes up, so the current is circulating truly in this direction. So the magnetic field inside is pointing up, as correctly noted in here. But as this comes down from north to south in here, so it should be coming down this way, okay? But that's the only minor thing, but it's still zero anywhere for an infinite long solenoid because of the fact that the edge effects do not show. So this will curl around infinity, come back to it. So as far as we're concerned, immediately next to the solenoid, it's still true, the magnetic field is B is equal to zero. This is not a problem for the toroid because of the fact that the magnetic field outside is zero because of the fact the currents in and the currents out are canceling one another, and the magnetic field inside is zero, so that does not have a problem whatsoever. The magnetic field inside has this circulation, which is correct, okay? There was only a sign issue in here when after I did it, I remember that that was wrong. Because in a practical solenoid, this will have a definite magnetic field outside, albeit immediately next to it is going to be negligible. But that direction will be then very important, trying to track it down because it's going to circulate in a full circle. So that's the only thing we did so far from this chapter. So now we're going to have this design. So I'm going to go back into the design of the solenoid that we had before. So we have a solenoid. Again, let me copy this because it's much easier to copy it and actually move it more or less. Let's make it longer because we're going to make some drawing in here. And again, this is the shape that I argued earlier for. Okay, so this one needs to move slightly. Can I use the arrow to move it? No, I can't. Okay, that's perfect, actually. Let me draw another line in here. So this is the shape that we're building our solenoid on. Again, we're going to bring some wires in here and wrap them around, just like we did before. So we're going to have this wire wrapping around the solenoid, coming back in here, wrapping around the solenoid, coming back in here. I'm doing the spaces in between them for a purpose, okay? And then it comes up in here. Again, there is a current, just trying to make it so that it's coming out this way. So I'm gonna make it coming from this way. So this is my current I. It's going to go this way. So in all of these sides, it's going to circulate in this fashion. And then when it comes out from the other side, it's going to come out from the other direction. In the same time, I'm going to wrap another bunch of wires around it, okay? We're going to choose a different kind of color in here. And this is the wire I'm going to wrap in here. So it's going to come from this side, going to have in here. This is what we call a transformer. Obviously, there are more blue lines. Oops, I didn't mean to do that. There are more blue lines coming out that are coming in, okay? So there is, the red one is called the primary, actually. This is a primary. And this is a secondary. So this is a typical transformer. So let's try to understand. So first of all, what's going on for a transformer? The current in the primary is changing, it's time dependent. This is time dependent. This is a function of time. And because it creates a magnetic field, I'm going to assume that this cross section is A. Okay, the area here is A really, okay? So what's going on in here? We have a current I that is time dependent, that changes. So this current, I'm going to also call the number of turns in the primary to be N1. And the number of turns in the secondary is N2. You can clearly see that N2 is greater than N1. Usually it's the other way around. Usually N2 is less than N1, okay? And we'll talk about that. But it could be also that N1 is more than N2. So the number of turns in here, actual turns. This length from top to bottom, I'm going to call L. And it has to be lowercase l because I need to introduce an uppercase L shortly. Can I write lowercase l? Okay, good. Okay, so this is the length of the solenoid. So if I want to find how many turns are per unit length, namely N1, this will be just N1 over L. So this is the number of turns. I hope that you guys have your piece of paper and you're following, okay? Because you can always read the book, but you are writing also as we're doing this so that you understand where this everything is coming from in here. So this is the number of turns per unit length in the primary. Okay. So this is basically the setup for the problem. Obviously, there will be a magnetic field, and the magnetic field for the entire, because if I changes with time, it doesn't matter if it changes or doesn't change, the magnetic field in the primary created by this N1 turns per unit length is going to be mu naught times N1, this little case N1, which is N1 over L times the current I, which is I1. So this is the magnetic field created by this current. At this point, I really don't have any current in the secondary. Okay, I don't have anything in the secondary. If the current I1 is a steady current, there is nothing in here in the secondary. You don't see anything in here in the secondary. But if I1 changes with time, the flux of the magnetic field, phi in the magnetic field in the secondary, is going to be the number of turns in the secondary times this magnetic field times the cross section, because this magnetic field is throughout the entire geometry in here. So times B times A. So this is the flux in the secondary, because I have N2 turns in here. And each one of them, there is a B current, a B magnetic field that running through them. And this is the cross section that they are in. So in this situation, if this current I1 changes with time, the magnetic field changes with time. And if the magnetic field changes with time, the flux phi2 changes in time, which will create an EMF in the secondary given by X equal to minus d phi 2 over d1, dt, I'm sorry. So there will be an EMF in the secondary. Now, if I connect it to a resistor and everything else, there will be actually a current in the secondary, I2. Provided that this current I1 changes with time. If this current does not change with time, there is always a flux in the secondary, but this flux is not changing with time, so therefore its derivative is zero, there will be no EMF. So condition for a transformer is that it works with time varying currents. So in order for a transformer to work, the current better be a time changing current. If the current is not time changing in the primary, nothing is going to happen in the secondary, okay? There are some problems in here that are going to be clearly related to this ratio in here, the EMF. Obviously, the EMF is going, B times A is actually the flux on a single turn, but I have N2 of them. So this is actually going to be N2, the EMF in the secondary, going to be N2 times the rate at which the flux phi B on a single turn. Phi B on the single turn is the magnetic flux, magnetic field times the area, that's it, okay? So this is in a sense what's going on in terms of the EMF. I'm sorry, with a negative sign. I'm sorry about the negative sign, okay? Now, I could do the same thing and look at the EMF in here in the primary. If this flux is to change with time, if this flux is to change with time, the EMF in the primary will be equals to minus the number of turns in the primary. So if somehow the magnetic field is changing one way or the other, doesn't matter. Current is causing it, doesn't matter what causes it. The magnetic field is going to change. So there will be actually an EMF in the primary given by the same law, but it's in N1 turns times the rate at which the flux per turn is changing. So in other words, the ratio of the EMF of the secondary over the ratio of the EMF in the primary, or if you wish, the voltage across the secondary over the voltage across the primary, is just as simply of the rate of the number of turns on either one of them. So you could have V2, or delta V2 if you like to call it, equal to N2 over N1 times delta V1. This number could be more than 1 or less than 1. Your initial voltage could be, for example, 120 volts, and your ending voltage could be 5 volts if you want to. If you play with this number N2 over N1 so that it's 5 over 120. So this would be a step-down transformer. Actually, it's this condition. When the ratio of N2 over N1 is less than 1. When the ratio of N2 over N1 is more than 1, let's say, for example, you have 100 volts, and this ratio is 10. So the end result in here, the voltage is going to be 10 times 100, which is 1,000. So in that case, it's going to be 1,000 volts. That is delta V2, and this is delta V1. So the voltage could be increasing. So this would be actually a step-up transformer. Most of the industry use step-down transformers, though. So this is the step-up transformer, whereas the first one is a step-down transformer. Your phone charger, every device that you have in your house is actually a step-down transformer. You have an AC voltage that comes in 120 volt delivered to your household, and you connect it to any device that you have in there. It needs to bring the voltage down to whatever. The computer works with 18 volt, depending, not the computer, the laptop, 18 volt. Some of the computers, they have some different voltage requirements, and all of them, they have that requirement. And your cell phone probably is a 5 volt charger, and so on and so forth. So those are step-down transformers. It's just the power company that use step-up transformers because they produce tremendous voltage and they have to amp it up to send it through the power lines so that when it comes to your household, if your neighborhood, there is actually a big transformer, sometimes actually on the power line itself, there is a big transformer, sometimes actually on the ground, where they have transformers that deliver power to their entire neighborhood. Again, it requires an AC current. Otherwise, this whole thing doesn't work because of that derivative. Okay? If this derivative is 0, it doesn't matter. You'll have 0 over 0, then identity, and it's going to be a there is no way it's not going to work in here. So you have to have an AC current for it, or a current that changes with time in order to have this thing works. So that is basically, in a nutshell, the idea of a transformer. You will have some problems on transformers, but that's not really the biggest bulk of this chapter. The biggest bulk of the chapter is still coming. So again, this is a simple relationship between the voltages, and you might be tempted, hey, how about the current? The current are actually going to be the inverse. So step-up transformer for the voltage is actually going to be lowering the current, okay? And a step-down voltage is going to amp up the current. That's why you have to have protected devices, usually near the power supply of anything, okay? Where is the power supply? Here is the power supply in here, okay? For this device, here is where you plug in the device, actually. Most of the times you'll have all kinds of protections in here, like capacitors to take some of the extra charges and dissipate them, and some of the stuff in here to take care of the currents and bring down the voltage for the operation for this one. Any transformer, any charger, you know, the charger. I don't want to put the charger of the monitor in here, otherwise the whole thing would go blank on me. Any charger that you connect to the wall and connect to your device is actually inside of it, there is transformer, okay? So, and that is really the idea behind it. It does not create energy when you go step up. You step up the voltage, but you kill the current, so the power is still the same. So that is something that you have to remember as far as transformers are concerned. At the end of the day, once the AC current is brought down to an operational level for your device, then it's going to go through a regulator to bring it into an DC current. Then your device is ready to use that voltage at that point. Anyway, so this is an introduction to transformers, which are important components in circuitry. I'm going to have another thing in here, just to look at this device in here, to look at these expressions in here. Let's try to understand what's going on. If I vary my current inside, I1, then of course the magnetic field changes, and which in turn means that the flux in the secondary changes also by virtue of this relationship. So what I'm going to call in here, I'm going to say that there is a connection between the current in the primary and the flux in the secondary, and that connection is what I'm going to call as the mutual inductance. So the mutual inductance between the primary, so it's basically there is a linkage in here. There is a flux linkage in here, linking the two in here. If it varies somehow, that is what's happening in here. The voltage in the secondary changes. Actually, the flux in the secondary changes, I should say. So the flux in the secondary, I can call it as being simply equal to, related to the primary. What's happening in the primary? By this relationship. So if you vary the current in the primary, the flux in the secondary changes. That's it. That's all there is to it here, okay? In other words, if I want to find the EMF in the secondary, which is just to minus the change in the flux in the secondary, is going to just minus this mutual inductance, which I'm going to call mutual inductance, because it's using really an inductance. There is no real connection between the two. Wireless chargers use inductance, by the way. If you put your device without plugging it in, the current changing in the primary circuit, and there is actually corresponding circuit on the other side, the flux of the magnetic field is changing, which induces a current in the secondary, and that is how you charge your computer wirelessly, or your phone, or whatever you're doing wirelessly. So this is the mutual inductance, and it happens without any contact. There is no contact between the blue wires and the red wires. Okay, there is only the flux of the magnetic field changing in one because of the current changing. that causes the secondary to have actually current in it, okay? So this is what is called the mutual inductance, M. So it's minus M times dI1 over dt, okay? So if you vary the current, then you will have an EMF in the secondary. Obviously, what is a secondary can be a primary, or what is a primary can be a secondary. I could do the same thing. I could have a current in here in the secondary, vary it, and in doing so, I will have a current in the primary. So what was my secondary can become my primary, and what was my primary can become my secondary. And what used to be a step-up transformer can actually become a step-down transformer, and vice versa. Because there is a perfect symmetry between the two. For that, there is actually a theorem in this branch of mathematics that says actually the mutual inductance between the secondary and primary is the same thing as the mutual inductance between the primary and the secondary and primary. So it's the same thing, in other words. Both of them are called M in this case, okay? The units for M, as you can clearly see, are the same units of the flux, which is the Weber, which is magnetic field times an area, which is Tesla times meter squared, divided by the units for the current, A for amps. So this is the unit for the mutual inductance. The mutual inductance, or M in general, is going to be a Tesla meter squared per amp. And this is, by convention, is called the Henry. So the Henry, instead of calling it Tesla meter squared, and a Tesla actually is not a fundamental unit. Tesla has some relationship between the currents and everything else. If you guys remember, a magnetic field QV cross B, or QVB, is equal to Newton. So it's force, really. So this is a Coulomb, and a Coulomb is amps divided by second. So this is an amp divided by second times a meter divided by second times a Tesla is equal to a Newton, which is a kilogram meter per second squared. Okay, cancel the second squared, and you will have the Tesla as being kilogram, cancel the meter, what is it, kilogram per amp, okay? So again, you can put the kilogram per amp in here, and it's going to be actually a kilogram meter squared per amp squared. So this is the Henry. Again, instead of calling it kilogram meter squared per amp squared, we just call it a Henry. So this is the unit for the mutual inductance. So from now on, we have another unit, and like, for example, the Farad, for Faraday, for the capacitance, this is uses a different unit in here for the mutual inductance, which is called the Henry. So again, I'm going to drop the symbol to 1 because, as I just said, there is a relationship between the two. So it's just the mutual inductance between the two, between the primary and secondary in here. It doesn't matter which one is which, okay? Because I could rearrange the whole thing and M does not change. As a matter of fact, I can calculate its value for this circuit, for this geometry. Let's calculate it. Because we have B, we have its value. B is equal to mu naught times N1 over L, the length of the wire, times the cross section. Please do not confuse the cross section A with the units for the currents. This is amps. This is the unit for the current, and this is an area in meter squared. Okay, this is the flux of the magnetic field. You have to multiply that, and you have to multiply it, of course, by I1. So this is the value that we saw in the beginning. Okay, I'm sorry, this is actually already the flux, not the magnetic field. I multiplied by the area. Okay, so this is the flux of the magnetic field in that one, and of course I have to multiply it by N2 in order to find the flux in the secondary. So the flux in the secondary, phi2, I have to multiply this whole thing by N2, which is mu naught N1 over the length of the solenoid times A times I1. Obviously, if I compare this expression to this one, this is M times I1, and this is the whole thing times I1. So that means that the mutual inductance in here is going to be simply equal to mu naught times N1 times N2 divided by L times A. It is clear from this geometry, this result you might need it for your some of the problems that we will be working on. Again, that if I switch N1 and N2, it doesn't matter. This is so that's why in here it looks like it's true in this case that M1 is M12 is the same thing as M21, because all it does is just flip the order of the number of turns, okay? That's all. And the primary, secondary, because I'm assuming the length is the same and the cross-section is the same and everything else is the same. U naught is actually the material that is between them. This is one way of increasing the mutual inductance, and that is to change the material inside. I put the vacuum in here in the tube that we started with. That's why I use mu naught. If I have a different material with different permeability, then I'll have to use its value, which is going to be more than mu naught. So I could change that value in here by playing inside what's going on inside the material in here. So that is basically the mutual inductance. I hope that you guys remember that every time I put something in a big square or big rectangle, that means that result is important. So you really need to write it down and try to think of means of using it. So this is one of them for the mutual inductance. So again, depending, give me N1, give me N2, give me L, give me A, I'm going to give you what the value of M is, okay? The typical values of M are some of the millihenry, okay? 10 to the negative 3 henries, not like the farad, which were 10 to the negative 6 or 10 to the negative 9 farads, okay? So this is a typical value for the henry, for the mutual inductance. And mutual inductance, as I was saying in here, if you're worried, how does it look like on a circuit? I was showing you that. This is how it looks like. It's this material in here. That is actually the wrap around these things in here. And that is actually self-inductance, which we'll need immediately. The self-inductance is just like the mutual inductance, but it's the wire wrapped up on itself, that's all, okay? So that is actually what we're going to introduce immediately, and that is the concept of self-inductance. So for self-inductance, anytime there is a wire that wraps, actually have the same thing. So it can have a flux that changes with the current inside the wire itself. I'm sorry. Okay. So this is the self-inductance. Sometimes we drop the word self completely and we just call it inductance, period. So this is the inductance. So this is the same wire. You wrap it around, you vary the current in it, and it's going to oppose a change in the current because there will be an EMF in here. That is, why do I have a minus in here? I'm sorry. I didn't mean for the minus. Do I have any minus in here? No. That's correct. There is no minus in there. It's actually coming from the EMF, the minus. It's minus d phi over dt, and that is equal to minus LDI over dt. So now there is a minus in here, okay? So the EMF the self-inductance opposes the change in the current. So if you have a wire, somehow that is, did I have a wire earlier in here? I don't know where I put it. Like this one in here, this is actually a self-inductance too, because it's the same wire wrapped around. So this will oppose the change in the current as it. If there was a current in it, it wants to keep it steady. Because if you take di over dt equal to 0, you're in good shape. There is no EMF. There is no opposition to that. There is nothing. But if if I starts to go up, there is an EMF that is going to oppose that. If current tries to go down, there is something that doesn't like it, and that is this one. So the self-inductance opposes, or an inductor opposes the change in current, not the current, not like the resistor. The resistor opposes the current, end of the story. This one opposes the change in the current. As you can clearly see from the derivative in here, okay? What happened to my wire? Wrap it around here. Any wire, you have it, if it's straight, that's not an inductor. At this point, it behaves like an inductor, the minute that there is turns. So when you're building a circuit, usually this is a very, very small value. You don't worry about it. But if you have a lot of it and it starts to go around, then you might have a problem with your circuit. Okay, and that is the self-inductance. And usually that's a problem when you're doing big electronics and you're trying to build stuff. So you have to be very careful with your design. And that is because that self-inductance can come back and hurt you. As a matter of fact, every time there is a kink in the circuit, you have to be worried about it because there is a wrap in here, okay? So, and that is the value that we're talking about in here, LdI/dt, and that is the self-inductance. We don't call it self. Again, from here, we're going to call it inductor. That is exactly what we mean by it. This is how it looks like. So there is a current in here, steady. There is no problem. dI/dt is 0. The minute you change the current, this is no longer 0. And the minus sign in here says that this doesn't like the fact that you changed it. So it goes up, it doesn't like it. It goes down, it doesn't like it. It wants to keep it steady. So if there is a current in an inductor, there is an energy, because if you would want to change it, it requires work from you because this doesn't like it, okay? If there is a current in an inductor, it requires work to change it. So let's see how much energy is stored in an inductor. Energy stored in an inductor. So assume with me for a moment that there is already a current going on in the inductor, I. Okay. Now I would want to change this current from I to I plus dI in dt amount of time. Obviously, the rate at which I'm doing this is dI/dt. So that's going to cost me power. And let me tell you what the power is. So the power needed to cause this change is actually voltage times current. So this is basically what that is, what the power is. And the voltage in this case is this EMF. So the voltage in this case is this EMF. The voltage is minus LdI/dt. Since I'm looking at the power in absolute value, I don't care about the sign at this point, okay? So this is in absolute value. I need to know how much it takes, and this is how much it takes in terms of power. So this is the voltage times I. So this is the power that we're talking about in here. Obviously, the power is defined as the amount of work or energy per unit time. I'm going to integrate both sides to find what the energy stored in an inductor. So I'm going to address it with the letter L in here because I want to refer to it as an inductor. The energy inside an inductor. Again, if you take the derivative with respect to time of 1/2 of I squared, if we do the chain rule and all of the stuff, I mean the product rule in this case. So the two drops. And then you will be left with an I dI/dt, and dI/dt is exactly this product. So the 2 cancels the 2, and this is exactly this product. So I dI/t is just the derivative of 1/2 of I squared. So what this rate of the energy in an inductor is 1/2, or at least the derivative with respect to time, of 1/2 of Li squared. Okay. Because if you take this derivative, we're going to end up with the same quantity in here. So that suggests, if I integrate both expressions, that the energy inside a conductor and inside an inductor is going to be equal to 1/2 of Li squared. So this is the energy inside an inductor of current I and of inductance L. Remember, L has the same units as M. Is also in Henry. As a matter of fact, we can go back and find the self-inductance for the shape that we have in there. For this shape. Okay, it doesn't matter which one of them, because only one of them is going to be self-inductance. So we're going to ignore the blue in this case. So if we go back into our geometry in here and draw it again, but this time only with one of them, it doesn't matter. So I'm going to draw with one of them only. So it's only one wire at this point. So this length is L. Okay. This cross section is A. Okay. And I have a current I in here, and everything is. So if I apply the same rules as before, the magnetic field now, according to this expression, B is equal to mu naught. So I have N turns now, because there is no need for N1 and N2, because I only have one basically type of turns in this case. Okay. So it's going to be mu naught N divided by L times the current I. And there is only one current in this case. Okay. So this is the magnetic field. The flux in here for the magnetic field per turn is going to be mu naught N times the area A divided by L times I. So this is the same area in here, and L is the length of the solenoid. Now, the flux that is going to be in the secondary now, which is the same as the primary, is going to be equal to N times flux per turn. This is per turn. But I don't have only one turn. I have actually N of them. So it's going to be N times phi B, which is going to be mu naught N squared over L times A times I. So in this case, the self-inductance is going to be just the multiplier of everything in here. So L is going to be mu naught N squared times the area A divided by L. This is like the capacitance. We were able to find the capacitance involving epsilon naught, involving the geometry of the capacitance, which was the area of the capacitance and the separation between the two plates. Here, it's related to the number of turns, the engineering, basically how you design it, depending also on the mu naught, which is what is inside that instead of epsilon naught in that case, and then also depending on the area of the, which is the geometry and the length of this one. So this is again the self-inductance or the inductance period of this solenoid, of a solenoid. So you have to be specific now. If it's a different shape, like for example, the one that I introduced, it's going to be different. So this is, it's still going to depend on mu naught. It's going to depend on R, the radius, the inner radius and the outer radius, and is going to probably depend on the that is going to be it, because that's going to be a measure of the cross section of how thick it is, plus of course mu naught plus the. So that is basically how these problems are set up in here. It's similar in a sense. There is parallels between capacitors and inductors when it comes to how you make them. So this is that one. As a matter of fact, I'm going to go back to the expression of the energy now, which is 1/2 of Li squared inside this capacitor and see, and this inductor, I'm sorry, and see what's going on. So the energy inside an inductor, let me write it down as big U, inside an inductor is equal to 1/2 of this L, which I'm going to explicitly write it as mu naught N squared divided by L times A times, so this is for a solenoid, okay, times the current squared. That's what we just found. Current squared times the L, and I just found the L in here. But I know the magnetic field in this case, B, is equal to mu naught times N over L times I. This result, we've used this extensively. This is the result we derived at that time. So this is the magnetic field, B. Now I'm going to find I in terms of B and sub it into this expression. And instead of expressing the energy in terms of the current, I'm going to express it in terms of the magnetic field. Let's see what I have. So from here, obviously, I will find that I is equal to B times L divided by mu naught N. So I'm going to sub it in this expression by squaring it. So I'm going to find the magnetic field, the energy inside an inductor U is equal to, first of all, I have that factor of 1/2 that popped up in there because of the integration. And then I have a mu naught n squared divided by L times A, mu naught squared, mu naught n squared divided by L times A, times the current squared. And the current squared has B squared in it, L squared in it, divided by mu naught squared in it, times n squared. Okay, I have some cancellations in order. I have the n squared and the n squared cancel. I have the L squared and the L cancel. And I have the mu naught squared and the mu naught cancel. So I have a bunch of cancellations, and let me rearrange the expression to look like this. So the energy inside the inductor looks like 1/2 of. So everything cancels. The only thing that is left in the numerator is A times L. And here is A times L. I'm going to write it at the end. What I'm left with is the magnetic field B squared divided by mu naught. Now, a few things in here. What is A times L? What is the area A times L? Does anybody know? For this solenoid.
Is it the volume?
That is the volume. That is correct. So this is the volume of the solenoid. So this is the volume of the solenoid. As a matter of fact, this is the volume where the magnetic field is. Because if I assume that this is long enough, then this is the region where the magnetic field is. In other words, the magnetic field anywhere outside is 0. So this is the region where the magnetic field is trapped, where B is trapped. Okay. So what I'm going to do, what we did a long time ago, if you guys remember, I'm going to divide by this volume. And I'm going to define the energy density in this case for the magnetic field, because this energy is in joules, by the way. Everywhere up to this point was in joules. So I'm going to divide by cubic meter, which is the volume in this case. So I'm going to define the energy density, U, for the magnetic field now, is equal to 1/2 of B squared divided by mu naught. This is a very important result. First of all, none of the properties of the solenoid are there anymore. The area doesn't appear, the length doesn't appear, the volume doesn't appear. So this is an energy density, which means the units for it are joules per cubic meter, not joules, okay? So if you have a region in space that has a magnetic field, it has this much energy in it. This is similar to when we did the electric field, when we did the capacitor. We found if I have a region in space that has an electric field in it, it was 1/2 of epsilon naught E squared. And I said then and there that you guys watch when we get into the magnetic field, we're going to find a similar expression. And we even predicted the shape for it. We said because this one has a half, probably the next one should have a half in it. This one has the electric field squared. This one probably should have the magnetic field squared. This one, and everywhere we dealt with the epsilon naught, the permittivity of electricity, it was always in the denominator. Everywhere you have 1/4 pi epsilon naught, or Q over epsilon naught, or something over epsilon naught, or something. Always epsilon naught was downstairs. The only time it showed up upstairs were in the energy density for the electric field. And I said that maybe that's going to happen also for the magnetic permeability, because the permeability was mu naught times I, was mu naught times something, and there for the definition for the for Biot and Savart law. Everywhere we dealt with mu naught was actually in the numerator. Today, it went downstairs. It went in the opposite direction. So it came to the energy densities, both of these two terms flipped on us. Okay. You guys see the similarity between these two. It looks like there is a one-to-one similarity between the two. This one is in joule per cubic meter, and this one is also in joule per cubic meter. This has the electric field squared. This has the magnetic field squared. Today in physics 4C, we actually did the Young experiment, the double slit experiment, and during that derivation, we found the intensity for the light on a path that is outside of the central, basically on screen. It was, and we said, okay, when we do physics for B, for some of them, we're going to see that the the intensity is proportional to the square of the field, of the electric field in that case, and it is. Okay, I said we're going to use in chapter 32 because physics 4C was a little bit out of sequence with physics 4B, but this is where that result is coming from physics 4C, for those sitting in physics 4C with me or sitting somewhere else in physics 4C, or who are planning to take physics 4C, you need to remember this result. Not only that, but we're going to need it actually in chapter 32, okay? So these two results are extremely important for the energy densities, meaning if I have a region in space that has an electric field or magnetic field, or both of them, I have a bundle of energy per unit volume. You take a big volume, you have more energy, and a small volume, you have less energy, because you have to multiply by the volume in here. And in this case, we started with the capacitor, and then the geometry of the capacitor disappeared, and we said this is a general result. Same thing in here. We started with a solenoid, and the geometry of the solenoid was in, but now the geometry of the solenoid is not there. Therefore, this result must be true no matter what. This is the principle of antennas. That's how your antenna captures signal from the ambient electric field and magnetic field, and if it is the right frequency, it's going to amplify it. As a matter of fact, today we're going to discover a circuit that might help us do that, okay? So far so good, everybody? Okay, yes. Very good. Very good. So we have learned a lot today so far, okay? This is the energy density. It's extremely important. I mean, this is the energy, I'm sorry, inside the inductor, which is very important, okay? We also learned about the transformer, which is a big deal, okay? This is actually transformer and how the voltages can go up and down, step up or step down the transformers. And we learned also about the energy density for the magnetic field and how it is similar, I mean, awfully similar to that of the electric field. There is indication that these two things, they look very much close to one another in behavior and everything else, okay? And then we saw also the inductance. I don't know if I wrote this one in here for solenoid and how to find inductance, similar to how to find capacitance in before, okay? So this is actually an important result too. So that is basically the whole argument that we're building so far. So let's put these things in circuit. So the symbol for the solenoid, which is another device, let me put the stuff that we learned so far. A resistor looks like this. Okay. Capacitor looks like this. Inductor looks like this. We use the letter L for it. Okay. Sometimes you will find it a little bit different, presented differently, but that's what an inductor is. A battery looks like this. So this is the plus, this is the minus, and one device that we used extensively, namely the switch. Okay. So these are the main devices that so far we have learned. Okay. Transformer, we're probably going to use it at some point, but if it does, it's going to be like this. Okay. With the two lines parallel in between them. So it's kind of complicated a little bit, but that's how the inductor, the mutual inductance, the transformer is, and usually there is an M in there, okay? So this is basically this devices that we're so far accustomed to. We're not gonna do much electronics with this one, although it's a very important component in the circuitry, but usually near the power supply, okay? This is the ones that we're gonna be dealing with. So we're gonna do, the first one we're gonna deal with is the RL circuit. So imagine with me, you have a resistor, and you have an inductor, L, and you have a battery with an EMF epsilon, and of course, for timekeeping, we have a switch S, okay? So this is the devices that we have in circuit, and again, we're going to use Ohm's law. There is a problem, there is a Kirchhoff's rules. There is a big problem here. We're going to ignore that for right now, but down the road, we will have to develop that discussion because this is not really how should I put it? the voltage drop in here, if there is a voltage drop, is not an electrostatic voltage drop between these 2 points, but it's going to oppose the change in the current nonetheless, okay? So what I'm going to say in here, after this one is closed at t equal to 0, S is closed. So at that point, there is no circuit. I mean, there is no current in the circuit. I is equal to 0, okay? And now we're trying to build the current in the circuit. As we're trying to build the current in the circuit, the current starts to grow, but the minute it hits this point, it's going to be opposing that change. So there will be a drop in voltage in here minus di over dt. The drop in voltage in here is minus Ri. And in here, there is actually, if I go in this direction, following the current, I'm going to be rising in potential. So this will be a plus EMF. So if I start from any point, it doesn't matter which. So let's start from here. We're going to hit the drop in voltage, I'm sorry, minus Ri, minus LdI over dt, plus the EMF is equal to 0. So this is Kirchhoff's rule in a simple way, simple fashion, okay? For this simple enough circuits. With this condition, that the minute we close the circuit, at that point, there was no current in the circuit. When we close the switch, I'm sorry, there was no current in the circuit. So if we say that, then we're going to play around with this expression and see its solution. So let's move everything to the other side. We'll move this term to the other side and this term to the, obviously this will be negative and this will become positive. So minus L di over dt is equal to R times I minus epsilon, the EMF. Take the R as a common factor in here. So it's going to be R times I minus the EMF over R, okay? And divide by this quantity in here and multiply by dt. So we're going to divide by, so we're going to multiply by dt and divide by L. Any mathematician in here would be horrified to what we're saying in here because the dt is not a number to divide by. It's a limit. So technically, we're supposed to say deltas first and then divide and then take the limit of the deltas going to 0. But we're going to skip all of that argument and we're going to go to the end of the story, which is just di over dt. I'm sorry, di over, and divide by this quantity also, and divide by I minus epsilon over R. So in other words, I will have on one side in here I minus epsilon over R, and on the other side in here, I would have a minus. Remember, I divided by the minus, and I will be left with an R over L, I'm sorry, times dt, okay? Well, I'm going to change a variable or do whatever you want to call it. I'm going to call U equals, not the same U, not the energy density, okay? If you really don't like that, let's make it W, okay? W, not omega, W. And hopefully it's not confused with the work either. So now we're running out of symbols, basically. Let's call it eta then. Okay? I don't think that we used eta this time. It's I minus epsilon over R, okay? Whatever you call it, okay? At the end of the day, the di will be the same thing as the eta. The point being in here is, this is constant. So I could have written this one similarly as d sub I minus epsilon over R divided by I minus epsilon over R. That's the whole point of a variable change in this case, because we want the numerator and the denominator to have the same form. And because epsilon over R is constant, so it's the same thing. That's really what this whole thing is. So now, even if I don't do this change of variable, this expression hopefully is acceptable to you guys. If it is, then I'm going to take the integral. On this side, I'm dealing with the integral of d eta over eta. And what is the integral of dx over x? Because that's exactly what this is. Isn't this something we saw before? What is this integral of dx over x? Somebody put something in the chat, and at this point, yeah, okay, that sounds right. That's a natural. Does everybody agree with Martin? Think it's the natural log. Okay, very good. So yes, that's correct. So that's the natural log of eta, and eta, remember, is all of that thing in there. So it's going to be ln of I minus epsilon over r is equal to, and the integration, you're worried probably, where did I take it from? I start from t equal to 0 to some t in the future, okay? So, so from t equal to 0 to some t in the future, okay? So that is the boundaries of integration. At t equal to 0, I was equal to 0. Or let's do just an indeterminate, okay, forget about the boundaries. Just find the antiderivative and that's it. So we're going to add a constant to it, okay? So there is a constant plus the derivative in here, the antiderivative of this one, which is dx, which is minus r over lt, okay? Take the exponential of both sides, the exponential of a constant minus this exponential. So this is just this exponential times the exponential of a constant, which is just another constant. So that is basically what this thing is. So it's I minus epsilon over r is equal to some constant times x, which is not necessarily this constant, by the way, it's any other constant, which is the exponential of that constant, times minus r over L times t. It doesn't matter at this point, call it a constant, but we're going to find that constant immediately. As a matter of fact, I can write I to being simply epsilon over r plus that constant times the exponential of negative r over Lt. I know at t equal to 0, there was no current. I know at t equals to 0, this is I sub t, by the way, as a function of time, that I sub 0 is equal to 0, which means that epsilon over r plus a constant times exponential of 0, which is 1. So this is 1. Constant plus epsilon over r equals to 0. That means that constant is simply a negative epsilon over r. So we have found the solution in here for the current in general. I sub t is going to be epsilon over r times 1 minus exponential minus r over L t. I know it looks similar to the charging of the capacitor, and it is. Except there you were building a charge in a capacitor. Now you're building a current in the conductor. That's the only difference. In there, we had Q of t is equal to some epsilon naught divided by, or C times epsilon naught times 1 minus e to the power t over RC. And here, tau, the time characteristic, is L over R. That is something different than before. So this looks like it's exponential minus t over tau, where tau is L over R, okay? And then, since it's a current, it must be a voltage over an ohm, and it is. So that is the difference between the two. So this is basically one way of looking at this one in here. So this is the buildup of a current inside an inductor. Once the current is going through, as a matter of fact, at that point, there will be no more changes. If we wait too long, if we wait t equal to infinity, when t goes to infinity, at that time, the exponential goes to 0. Which means that the current becomes steady. At that point, the current becomes just epsilon over r. And this epsilon over r looks very much similar to just an EMF and a resistor. That's all. This is how the circuit at the end would look like. You have a resistor R, and you have an EMF, and that's the end of it. So what happened in here? It behaved just like a wire. So again, when they tell you that there is a circuit that has been open for a long, closed for a long time, then take the inductor and replace it with a wire. That's it. So for a long time, okay, the inductor becomes just a wire. Immediately, it will become an open circuit. It's an open. And here it's short-circuited. So this is a hint on how to do some of these problems. If they tell you that the switch has been closed for a long, long time, and any time you see an inductor, replace it with a wire. That's it. like in this situation. Immediately, though, the current is 0 because at equal to 0, 1 minus 1 is 0. There will be no current in the circuit. Why? Because this is behaving like an open circuit. This is opposite to what the capacitor was doing, actually, if you guys remember. If I'm dealing with the capacitor, and if it says that after a long time, the capacitor will become as an open circuit. It's opposite, because the capacitor, after a long time, will be fully charged and will not allow current to go through it anymore. Whereas in this one, after a long time, the current will be steady and it doesn't care at that point. It's not going to oppose, because it opposes the change. It doesn't oppose the current. Whereas immediately thereafter, there is a big push of current through the circuit trying to go from the battery. Immediately, when you close it, it's trying to push a lot of current through the resistor, and this doesn't like that. It's going to stop it. So it's going to behave like an open circuit, as opposed to a capacitor that after a long time, actually, it's going to be fully charged. That at that point is going to kill the current. But immediately, the capacitor actually behaves like a wire because it's going to allow current to go through. It wants to charge, so it wants to build the charge. So this is going to be short-circuited. So everything looks opposite to everything in here. Okay, so this is immediately around t equal to 0, greater than 0, but immediately next to it. And so this one is actually greater than, but very close from 0. The inductor behaves like an open circuit. It's going to open. So whenever you see it, just make sure no current is running through it. This is opposite to what a capacitor does in a circuit. So this is basically on how to build a current inside a capacitor. We still have a few times. So we're going to do the LC circuit. We're going to combine an inductor and a capacitor now together, and no resistor for the time being. LC circuit. Okay. So what's going on? Let's assume we have a capacitor Q, a capacitor C. And we're going to start with the charge Q naught actually on a capacitor. So there is a t equal to 0. Q is equal to Q naught. Okay. And then we have an inductor. I'm sorry, I should have probably pushed it in the opposite direction, but that's fine. Okay. Should have plus in here and minus in there, so that at least to see immediately what's going on in here. Okay. And for the sake of argument, we always need a switch at t equal to 0. We close it. So this is the switch S. So what I'm saying is this is at t equal to 0. S will be thrown to be closed. We close the circuit. Okay. There is no EMF now to worry about. We only have a resistor. We only have a capacitor and an inductor. That's it. So this is C and this is L. So as you can clearly see in here, the minute I close the switch, this whole circuit tries to build cancel. Basically, the capacitor tries to push a current to cancel the charge. So, but in doing so, it's going to push a current against this guy, against the inductor. The inductor doesn't like current change in the current, but it's going to resist that. And as the current starts to build up, then in this case, it's going to lose more and more charge in it. And as it does, the current is going to be established in the capacitor, in the inductor. Once this one runs completely out of charge in here, when it's completely discharged, there will be a current already in the inductor. So at that point, the capacitor is not going to push any more charges because it ran out. But the inductor, what we will do in this case, is going to push the current because it has energy, and the energy in it at that point will be 1/2 of Li squared. So it's going. So initially, yes, you're saying that I have a Q naught squared over 2C. That's how much energy I have in the capacitor. That's why it was pushing the current to begin with. But at some point, Q naught will cancel completely because Q becomes 0. So at that point, I run out of energy in here, but there will be energy inside the inductor, and that will push the current now to build the charge in the opposite direction now. until this becomes Q naught. And this will become negative Q naught. And at that point, this will run out of energy. The inductor will run out of energy because at that point, it cannot push any more current. That's it. It will consume all of its energy. But then it will have a charge now sitting in the capacitor, albeit in the opposite direction. So now the capacitor will push current in the opposite direction, but this will oppose it still and build up energy in the process. And this one will lose energy in the process, and at some point they will run out of all of these Q charges in the opposite direction, and there will be a current now going through the inductor. Okay. At that point, the inductor will step in to push the current, to continue pushing the current, because it doesn't like the current to change at all. The fact that this will run out of energy will mean that this one has to push the current until it runs out of its energy, and so on and so forth. You guys see that this process is not going to end. This is going to be forever and ever. That's why this LC circuit is actually called an oscillator. The reason why it's an oscillator is because it's the current at some points is going this way and some other points is going the opposite direction and so on and so forth. So immediately when we caught it, it's actually going clockwise. Okay, so let's try the law for this case. So what we're saying in here, we're writing dq over dt. I'm sorry, what am I writing dq over dt for? I'm writing the voltage. So let's take a point in here. Let's start from here to here. I'm going from negative to positive. So this is actually a rise in potential. Did I write it backward in here? Usually I write the drop in potential. For some reason I wrote it the rise in, no. Yeah, this is the rise in potential. Technically, I usually write Ri plus LdI over dt minus epsilon. It doesn't matter. At the end, it's going to be 0 anyway. And the minus will just flip in here. So same thing in here. So what I'm saying in here is the rise in potential is going to be Q. So at some time, T, Q is the charge across the capacitor. And I, so this is a time-dependent function, and this is also a time-dependent function. I is the current in the circuit. So what I'm saying in here is the rise in potential, which is Q over. So at some point in here, I have Q, and this will become negative Q, and there is a current I. So that's the point in here. So this is the initial condition. It changes with time, of course. So the rise in potential, which is going to be the drop in actually the, I'm going to write it as minus Q over C, because I'm going from the negative to a positive, which is rise in potential, and the drop in potential is Q over C. So this is a rise in potential when you change the sign to it, okay? But now I'm going from this position to that position, and this one does not like the change in the potential. And the drop in potential in this case, okay, is going to be minus times minus, so it's going to be an L di over dt. And this must be equal to 0. Okay. There is a relationship between the current and the voltage that I need to borrow immediately, because this is a discharge. I know that I is equal to minus dq over dt. So this will become actually a minus with the, when expressed in terms of the charge and the discharge in the capacitor. So it's going to be minus q over c minus L dq over dt. The second derivative, because it's already involves the first derivative with respect to time of the current. So if I want to find the first derivative of the current with respect to time, it's going to involve the second derivative of q with respect to time. And this must be equal to 0. Obviously, I multiply everything by negative and divide by negative L. So this expression looks like this: the second derivative of q with respect to time plus 1 over LC times q is equal to 0. Compare to mechanics. Compare to physics for A. Let me draw some comparisons in here because there is some parallelism here. This expression would look similar to F equals to MA for a spring. If A for a spring is minus Kx, where the spring constant. So this expression, if I move everything to one side, it looks like the second derivative of x with respect to time plus Kx is equal to 0. So this would look like the second derivative of x with respect to time plus k over m times x is equal to 0. So what do I have in here? If I treat x as q, position x is the same thing as the charge q, okay? The current I will be treated as the velocity because the velocity is just the derivative of x with respect to time. The mass m will be treated like L. Sorry, did I flip the directions? I'm sorry. I meant to say mechanics on one side. So the mass m will be treated as an inductance L, because that opposes the change in current, and the change in the current is the change in velocity, which is the acceleration. So the acceleration A is actually the equivalent of the rate of change. So the acceleration A is equivalent to the change in current. Okay, di over dt. So there is comparison, there are parallels between all of them, where M and L are similar. As a matter of fact, the capacitance 1 over C, not C, 1 over C is equivalent to spring constant K. The last thing that we need to worry about is the resistance R is equivalent to coefficient of viscosity. I don't know what symbol you use, but we usually use the letter B for it. Okay. If you do this, you can take a mechanical system and write it as an electrical system. As a matter of fact, this whole comparison that I hope that you guys see in here is basis to something in branch that is called a the word now is analog circuits. Imagine yourself, you have this problem in mechanics where you're supposed to test a building or structure, a big structure, okay? And you would want to test to see under what stresses that building give ways, under what stresses that building really stays stable, okay? It is very expensive to go and actually build the building and test it because it costs a lot of money to do that. So instead of what you do, you build an analog circuit to it. The building has this much mass, I'm going to assume that it's this much inductor compared to it. And you build the circuit in such a way the math looks similar. And then you send your signal. You send your excitation. You send whatever stresses the building is supposed to be under in terms of electrical signal, and see on an oscilloscope or whatever the display device what happened to the building, at least in the simulated environment in here. So you can simulate things. Before the advent of computer simulations, this was the way of simulating stuff. You use an analog circuit to whatever you're dealing with. So you make comparisons. As a matter of fact, it's still a viable option right now. You build it on a computer, you go through a lot of approximations, but then if you build it on a circuit, you go in the lab and you build the lab and you see exactly what's going on, and you see that the responses are tamed with these conditions, for example, with this much resistance, with this much things. So you can go now and build a model of it. to see if it's, so then now you saved yourself a lot of money under those conditions so that you know exactly what kind of stresses may cause a lot of problems. So now you can fix it, and then you're going to go and invest in a bigger model or actually build the thing. See, this is an analogy between the two. So my point in here also is the fact that this expression, we have seen it in physics 4A. If you have done this one, you have seen the mass spring system. And the mass spring system is exactly similar to what I was describing in terms of what's going on. So you have spring and you have a mass, okay, that is free to move. So at some point, you stretch the spring initially. That is the equivalent of the capacitor. Spring is the equivalent of the capacitor, except in comparison, it's 1 over C, not C. So you build a charge in it. So this would be the equivalent of an initial charge, which is the displacement. Remember, charge and displacement are the same. And you let go. So it's going to decompress in this case until there will be, it will become completely incompressed. And at that point, there is no problem. But this one has inertia. As a matter of fact, the fact that the inductor opposes the change in the current is right like the mass opposes the change in its velocity, which is the inertia. So this will keep on moving until it compresses the spring, and this motion goes back and forth, back and forth. The solution we know is some sort of a combination of a cosine and a sine function of omega t plus some b constant times sine of omega t, where omega is the square root of k over m. This is similar to that in a sense that this solution to this oscillator is similar. The only difference in here is because the maths are similar. They're 100% similar. The only difference in here, instead of omega squared being k over m, now omega squared is just 1 over LC. So the solution should be the same. The charge q as a function of time should be some amplitude times cosine of omega t plus some amplitude times sine of omega t, where omega in this case is 1 over square root of LC. End of the story. So this is the natural frequency of this oscillator. If you don't trust me, just take the derivative of this guy with respect to time. Once the cosine changes to a sine with a negative sign, pull an omega out. And in here, the sine becomes a cosine, pull an omega out. So there will be an omega out completely negative a times sine omega t plus b cosine omega t. Take the second derivative. When you take the second derivative, you're going to put another omega in here, and the sine will become a cosine. Remember, you have a negative sign in front of it. So there will be another omega, and you have an omega out. So it's going to be an omega squared. And in here, the cosine, because you took the derivative of a sine, it became a cosine. When you take its derivative, it becomes a negative, and the sine and the omega comes out. So it's going to be negative omega squared times the same thing in here, times this quantity. When you add to it, omega squared times that quantity is going to end up to be 0. So in other words, you just take the derivative. So here is the deal. Take dq over dt. It's going to be minus omega times a times sine of omega t plus b omega times cosine of omega t. All I did was take an omega out in here, and this is a chain rule. And the second derivative of q with respect to time is going to be a minus. And here I have an omega that's going to come out. So it's going to be omega squared times a. And in here, the sine becomes a cosine. And in here, the cosine is a negative. B times omega squared, again, because I have to pull another omega. And here, and the cosine becomes a sine. And this is minus omega squared times a cosine of omega t minus omega squared b sine of omega t. Now this, if I compare that to omega squared times q, remember, omega squared times q, this was omega squared times a cosine of omega t plus omega squared b sine of omega t, just by subbing in here the value of q, the way I have written it. And adding the two quantities in here, obviously d squared of dtq squared plus omega squared q is equal to, term by term they cancel, this two cancel, and this two cancel, and it's 0. Provided that omega, of course, is equal to 1 over square root of LC, as shown in here, because I have 1 over LC in here. I don't have that. So in this case, we have shown that this is actually the solution to my equation, where A and B are just general terms, constants, okay? They depend on the initial conditions. A and B, constants that depend on initial conditions. If you took differential equations or you're taking it, this stuff will be easy for you guys. If not, just follow the steps and it should be fine. Compare it to mechanics if you like, and it's going to be fine, okay? So the bottom line is we have found an expression for Q as a function of time, which is just A times cosine of omega t plus B times sine of omega t. I know at t equal to 0, there was no current in the circuit, and furthermore, Q was equal to Q naught. So I know at t equal to 0, Q sub 0 was equal to Q naught. So that tells me that A times cosine of 0 is 1, plus B times sine of 0, which is 0. So A is equal to Q naught. I need to also find the derivative of this guy because that's a current, I, which is minus dq over dt, by the way, in this case, because it's a discharge. So again, I have a minus A times omega times minus, so it's going to be a plus omega times A times sine of omega t minus B omega cosine of omega t. Okay, I'm going to plug in I sub 0 being 0 in the circuit because there was no current to begin with. So this is going to be omega A times sine of 0, which is 0, plus minus B omega times cosine of 0, which is 1. This must be equal to 0 because I know initially there was no current in the circuit. So this is 0 because 0 times A is 0. And this B omega is equal to 0. That means B is equal to 0. So the solution that we have found actually is the following. Q sub t is Q naught times cosine of omega t. And the current in the circuit actually, so it's time dependent and it's just a cosine. And the current in the circuit, which is very important, it's minus dq over dt. And the minus times minus becomes positive. So it's going to be Q naught omega sine of omega t. So the current is time dependent too, and it changes as a function of time, like this. So this is t. Of course, we started with the circuit being at t equal to 0, and this is the current I sub t. Okay, so it's a periodic, and the periodicity in this case, the period p or omega, first of all, is equal to 1 over square root of LC, which means that the period t is equal to 2 pi over omega, or 2 pi square root of LC. Okay, so this is really the characteristic of this circuit, and it's called an oscillating circuit because of this oscillator, because of this behavior. This could be the grounds of a lot of things that we will need in this thing. Okay, we still have quite a few things to do in this chapter, not too much, honestly. So we still have a few things to do. Hopefully we can finish them by Wednesday and then do some problems because there will be quite a few applications from this chapter. Okay, this chapter is very important, as I was mentioning in the beginning. And all the signals so far, although we ended up with an AC current at the end, I mean a time-changing current at the end, because it's like the mass spring system, similar to that analogy. But the power, the battery itself was actually an AC battery. I mean DC battery. What happened when it's an AC circuit, AC battery, then there will be oscillations with resonance and things like that. So next time when we meet, we're going to do the RLC circuit. Have you done these things in detail in mechanics? Have you done the harmonic oscillator, the dampened harmonic oscillator, namely you have a mass spring system and also a friction in it, namely viscosity. And you found this decaying behavior. You guys remember that or not? From Physics 4A? Okay. Okay, since you didn't do that, we'll probably have to get into it a little bit. Anybody else other than Martin? I mean, if it doesn't ring a bell, that's fine too.
To be honest, I don't remember it.
Okay, that's fine. Okay, so let's, we're going to get into this one in here because I was hoping that you have covered that stuff in physics 4A. If not, let me give you a nutshell basically of what we did in physics 4, or what you probably could have done in physics 4A. So basically what you have is, you have a spring, you have a mass, and in addition to that, there is viscosity, B. So in this case, the mass M and the spring constant K. And if you write the equations correctly, the equations according to F equals to ma. So this will be ma, and this will be the viscosity, which is proportional to the velocity, and this will be k times x is equal to 0. And this is a normal and enforced harmonic oscillator. The problem becomes complicated when you have a forced harmonic oscillator, when you have a force f of t on the other side, and that force could be a problem. So this will be the most general case of a forced harmonic oscillator. Okay, what forced means this factor F in here, and with damping. And this is the damping factor in here, the viscosity. Okay, we're going to do something similar to it. Oh man, we went a minute after. We're going to do an RLC circuit, which has a resistor, which is the equivalent to the damping. And then we're going to have an AC circuit. An AC circuit will act as your forcing agent in here in this case. And that is part of the lab. That is really one of the things, the big things you need to learn from this class. And that should help you basically with oscillators in general and understand what's going on with them and AC circuits and things like that. So we have something minor to finish on Wednesday, and then we do applications. And hopefully by Monday of next week, we're going to introduce the RLC circuits and things like that. Sounds good? I'm sorry about going 2 minutes over. Thank you. So I'm going to stop the recording.